Okay, hello everyone. Welcome back to the Ultra Quantum Matter seminar series. Today we will have two more short talks, each talk being again 24 minutes plus 5 minutes Q&A. So the first talk, we're happy to have today Sahand Seifnashri from IAS Princeton, who will talk about Lieb-Schultz-Mattis anomaly as an obstruction to gauging. Yeah, take it away.
Hello everyone. So thank you for the organizer for inviting me to give this seminar. It's a pleasure. So today I will talk about this work, which will hopefully appear soon in a couple of weeks. And please ask any question if something was really unclear or something. Yeah, it wasn't clear. Okay, so let me start with a short introduction. So the general goal is to derive dynamical consequences from global symmetries. So global symmetries can often impose a powerful constraint on dynamics of strongly coupled system, both in the continuum or on the lattice. So one of the earliest examples on the lattice is the LSM theorem by Lieb-Schultz-Mattis in 1961. And a very important example in the continuum is the 't-Hooft anomaly matching. So in the next couple of slides, I will define carefully what I will explain what the LSM theorem is and what 't-Hooft anomaly matching is. And one of the goals of this talk would be to make a direct connection between these two, between this theorem and this condition. So more specifically, I will show that all anomalies on the lattice can be thought as 't-Hooft anomaly. So, and I will focus only on bosonic theories in 1+1 dimension. Okay, so let me give you a definition of the anomaly. So the definition of anomaly could be different depending whether you're a high energy theory physicist or a condensed matter physicist, whether you're on the continuum or on the lattice. So I guess the least controversial definition in the continuum is the definition that a 't-Hooft anomaly of a global symmetries is defined as the obstruction to gauging that global symmetry. So that's the working definition of a high energy theory physicist in the continuum. However, on the lattice, the definition of anomaly is usually defined through the bulk boundary correspondence, which amounts to saying that anomalous theories live on the boundary of symmetry-protected topological phases. So what are the examples? The famous example is topological insulators, which have anomalous edge modes, which are protected by U1 symmetry and time reversal symmetry. So the topological insulator is the SPT, and the boundaries has anomaly. Another example, which I explained before, is associated with the LSM theorem. So what is LSM theorem? So LSM theorem states that, so let's consider a spin chain in 1+1 dimension with the following conditions. So consider a spin chain like the Heisenberg chain, which has SO3 symmetry, has lattice translation symmetry, and moreover, the SO3 is realized projectively on each side. So the Hilbert space is a tensor product of local Hilbert spaces, and each Hilbert space transforms in the spin-and-a-half representation of SO3, which is a projective representation. In that case, they proved, Lieb-Schultz-Mattis proved that the theory cannot be trivial in the sense that it cannot have a unique gap ground state. And later on, this condition was dubbed as a mixed 't-Hooft anomaly between lattice translation and SO3 symmetry. In the sense that you could also view this theory as a boundary of some SPT phase. So the goal of this talk would be to make a connection between these type of anomalies on the lattice and this definition of anomalies in the continuum. So the first goal is to give a microscopic formula for the anomaly for 1+1D lattice Hamiltonian systems, and the anomaly would involve both internal symmetries and lattice translation symmetry. And second, we will argue that the anomaly is the obstruction to gauging even on the lattice. So you could use the same definition that we used to use in the continuum to detect anomalies. So I will develop a method of gauging symmetries which are not necessarily on site, and I'll show that the obstruction to this gauging method is exactly the anomalies as classified in the continuum. So are there any questions so far? Okay, good. So this is some of the key references, and I apologize for the references that have not appeared here, But let me just mention, highlight this reference in last year by Natty and Mog, where this work is mainly inspired by, and I use most of the techniques developed in this paper. So the outline is the following. So I give you already the introduction. So next I will talk about topological defects, which will be the main tool for deriving a formula for the anomaly. Next, I will give you the formula for the anomaly and discuss gauging. And at the end, depending on time, I will give you two examples. The first example is the Heisenberg chain, and then I will construct non-invertible lattice translation symmetry from LSM anomaly. I'll give you one example. Okay, so let me begin with topological defects. So what's the definition of symmetry? Let's say we have a lattice Hamiltonian system in 1+1 dimension. So we define a symmetry as a unitary operator U that commutes with the Hamiltonian H. However, this condition is not enough. If you're in quantum mechanics, that's a good definition. But if you're in a lattice system and has spatial dimension, we also want to have a notion of locality. So we want to say that the unitary operator generates a symmetry if it acts locally, in the sense that it maps local operator around site J to some operator around site J if it's internal, or around some other sites if it's a spatial symmetry. So we want to have this notion of locality for the symmetry operator. Now the point is, to manifest this locality property, it will be extremely useful to represent symmetry operators by topological defects. So if you just given a unitary symmetry, you are not guaranteed that U maps local operator to local operators. But as I will explain, if you represent symmetries by topological defects, then this locality property is manifest. And importantly, I would not have time to explain, but there exists a one-to-one correspondence between symmetry operators and symmetry defects, even on the lattice. So in the continuum theory, when you have Lorentz invariance, this is natural because symmetry operators and defects are usually related by doing a Lorentz transformation. But it turns out that in lattice Hamiltonian system, even without any relativistic invariance, there is a one-to-one correspondence between them. Okay, so to define what topological defect is, let me just give you an example. So let me start with just transfer field Ising model. So we have a qubit per each site, and so J runs over the sites, and this is the Hamiltonian. We have sigma JZ, sigma J plus 1Z, and we have this term. So this theory has a Z2 spin flip symmetry that I define it by eta. So the symmetry operator is given by the product of sigma x's. And if you conjugate sigma z by this u, you just flip the sign of sigma. And this arrow in my notation is always means conjugation. However, you could also define a symmetry twist in space, which correspond to a topological defect. So the topological defect is the following. So you basically have to perform a symmetry transformation only in half of the space. So if I perform a symmetry transformation in half of the space, most of the term in the Hamiltonian commute with this operator, but I only generate a minus sign. So I only flip the sign of the sigma 1z, sigma 2z in the Hamiltonian. And I will call this the defect Hamiltonian. So this Hamiltonian describes the system with a single Z2 defect, where if I put my theory on a circle, this minus sign corresponding to an anti-periodic boundary condition. So I could have either periodic boundary condition on a circle, or I could use my Z2 symmetry to define a Z2 twisted boundary condition. And this is the Hamiltonian for that system. So this notation is important. So H of eta, it means that I have a single eta defect on link 1, 2. And that's the expression for it. So importantly, this defect is topological. What it means to be topological, it means that it does not matter whether I put the defect on link 1, 2 or link 2, 3. These two systems are unitarily equivalent. So there is a local unitary operator. So it's important that this operator is local, that allows me to move the defect by one site. So if I consider the system with a single defect at link 1, 2, which is this one, if I conjugate it with sigma 2 of x, I will move it one side to the right. So I will use this diagram more in this presentation. So this is the space-time diagram. So below I have a defect at this, I conjugate with this and I move it one side to the right. Okay, are there any questions so far about this notation terminology? Okay, very good. So now let me discuss the defects more generally. Let's say I have a system with a global symmetry G. G could be arbitrary internal symmetry. Now, I could also consider defects for this general symmetry G. So for each group element G inside G, I could define a twist in space, and I will denote it by this defect Hamiltonian and with this picture. So this picture, it means I have a single defect G at this link, and I denote it by this defect, which is a defect Hamiltonian for this system. Moreover, so for symmetry operator, we have group multiplication because multiply two unitary operator to get another one, and they follow a group multiplication law. So we could translate that into a fusion rule for these defects. So you could consider a system with two defects, one at link j-1j here, the other one at link j plus 1. So let's say I have a G defect here, H defect here. So this system should be equivalent to having a single GH defect here, because at the end of the day, this is like a twist. So if I do a G twist and an H twist in space, is equivalent to doing a single GH twist. So this is roughly like a gauge transformation. So these two systems are equivalent, physically equivalent, meaning that they are related by a local unitary operator. So I define this local unitary operator by this lambda of J, G, and H. So I call this a fusion operator. So it conjugates the defect Hamiltonian for two defects into the defect Hamiltonian for a single defect. So in equation, I have this. This is my fusion operator. And importantly, this fusion operator is unique up to a phase. So I could find this, but it has a phase ambiguity, because if I multiply it by a phase, it does not affect this equation. Okay. So now that I have defined topological defect, let me first give you a formula for the anomaly and then argue why this is an anomaly. So I'll first give you the final result. So you could detect the anomaly by using an F move. So the idea is the following. So you consider the system with three different defects, G1, G2, G3 as three different links, and I will fuse them in two different orders. So I first fuse G1 with G2, then here I move G1 one side to the right, and then fuse it with G2, G3, or I could first fuse G1 and G2 and then fuse them with G3. So I have two space-time diagram, and so the left-hand side is just the product of three local unitary operators. So the operation here is just lambda j, G2, G3, so I'm just fusing them here. On the next step, I'm moving G1 one side to the right. And then I will fuse G1 with G2 and G3 at side J. So the left-hand side is just product of these three unitaries. And the right-hand side is just product of two unitaries, these two. And if you take the ratio of these two unitaries, they commute with your Hamiltonian. And by definition, I assume there is no local operator that commutes with the Hamiltonian. So the expression on the left and on the right, they should only differ by a phase factor. So I find this phase factor F. So F of G1, G2, G3. So this is a phase, and I claim that this F is the anomaly. So one rough argument, which is a geometric argument, is because here basically we are doing two gauge transformation and they must differ by phase. But more concretely, I will show that this F is the obstruction to gauging G on the lattice.
Sahand, quick question.
Yes.
I remember in the paper by Michael Levin and Kyle, there was some subtlety, right, with defining this F. Somehow you had to make sure like that some geometric phases cancel out or that they have the proper gauge transformation properties.
Yes. So here, as you see here, the fusion is done at different sites. Here, the fusion is done at this site J, but here is done at site J-1. And this will be important later because you would expect that this is the anomaly, this satisfies the tricycle condition, but as I will show in next slide, the story would be different, and it is exactly because of that subtlety. And it will have a feature is that this F contains both the anomaly and the LSM anomaly, as I will discuss. So if you don't get your answer, please ask again.
Okay, thank you.
Thanks for the question. Okay, so before arguing why this is an anomaly, let me just tell you what are the properties of this F. So this F is basically a function of 3 group variable into U1. And importantly, it satisfies two important conditions. The first one is that F satisfied a modified pentagon or co-cycle equation. So I should say that in the continuum, this is roughly correspond to the West-Domina constancy condition for anomalies. So, and the equation is like this. So if this term on the right-hand side were absent, this would be the standard pentagon equation. But because I'm on the lattice and I'm doing the fusion at different sites, I get this extra term on the right-hand side. The second, because lambda j's have phase ambiguities, this phase ambiguity also propagates into ambiguity in F. So F is subject to this identification. So when I say F is the anomaly, F modulo this ambiguity, which in the continuum correspond to local counter term, is my anomaly, because sometimes I could cancel this anomaly by this phasor definition. So now let me tell you what these two conditions means in the language of group cohomology, which might be more familiar to some people. So the point is to define anomaly co-cycles. So if I take this F and divide it by FG1, G2, I define this omega and alpha. So the modified pentagon equation for F becomes the standard 3 co-cycle condition for omega. And this F of G1, G2, comma 1 will satisfy a 2 co-cycle condition. Moreover, I said that F has some phase ambiguity. So let's consider a system which has a translation symmetry. If I have a translation symmetry, I don't want to violate translation symmetry. So I would only consider phase redefinition which are J independent. So if you mod out by J independent phases, then you find the cohomology classes of this 3 co-cycle and 2 co-cycle. So omega, the cohomology class of omega becomes something in H3 of G, which we know it classifies internal anomalies in internal symmetry G, and then alpha becomes a 2 co-cycle. So I will argue that this alpha corresponds to the generalized LSM anomaly, and omega becomes the anomaly in internal symmetry G. Let me also mention that if we don't care about translation, we want to mod out by J dependent phases, then this completely trivialize alpha. So we could get rid of alpha and we would only left with omega as expected. So as I said, omega is the 't Hooft anomaly in G. I will argue it, and alpha is the mixed anomaly between G and translation. Max, does this answer your question?
Sorry,
okay, so now,
let me just ask a quick question there. If you don't care about translation, would your procedure give you a co-cycle at all? I mean, would it work?
yes.
You're
see
doing
that,
it at 2 different points. I'd worry maybe you wouldn't get cancellation.
So what will you will see? You will see that if you mod out by J dependent phases, so this omega and alpha will be J dependent, but the cohomology class of omega will still be J independent.
I see.
Yeah.
Thank you.
Thanks for the question. Yeah. But alpha, you will completely trivialize alpha. So yeah. So now to discuss why this is an anomaly, I want to first tell you a method of how to gauge the internal symmetry in general, even if the symmetry is not on site, and show you the obstruction to gauging is exactly this anomaly. So to do the gauging on lattice Hamiltonian system, usually is done in 2 steps. The first step involves adding gauge fields on links, and the second one consists of imposing Gauss law. So here, adding gauge field on the links here roughly correspond to, so each defect on each side correspond to a single gauge field or gauge variable on a single link. So if I want to make the gauge field dynamical, I have to add all possible defects on all possible links and take a sum over all of them. So to be concrete, let me consider when G is finite, but it can be done for G infinite. So if G is finite, basically I'm adding G dimensional Hilbert spaces on links. And then I extend my Hilbert space by taking copies of my original Hilbert space for each of these defect configuration. So here I have a periodic chain with L sides, and to this picture, I have a G1 defect here, G2 and GL, okay? So this is the extended Hilbert space. And the extended Hamiltonian has two parts. So there is the first part which acts on the degrees of freedom on site, and there is a part that acts on the degrees of freedom on links. So here, this is just a defect Hamiltonian, which describes G1 to GL defect. And the part that acts on the links is just a projection operator, which just fixes, just tell me what are the value of the defect. So this is the projection operator into G1 to GL. Is this clear? This definition of the extended Hamiltonian? Just keep track of the label for the defect. And now this fusion operator can be also extended like this. So I just on sites acts as before, and on the links acts as a projection operator. Now the key point is that now lambda tilde commutes with H tilde. Before it was conjugating two Hamiltonian to each other, but now lambda tilde looks like a local symmetry. However, it's not invertible because these are projection operator. But you could easily make it into an invertible operator. What you will do, you sum over A and B and consider this configuration. So I consider two AB defect, fuse them to A and B, and then split them into AG-1 and GB. And it's very easy to see that this generates a local G symmetry because these operators form a representation of G, and since they are made of lambda tilde, they commute with the Hamiltonian. So this is basically my local symmetry. So to impose the Gauss law, I just want to impose that GJG equals to 1 at all sites. So basically, I consider this projection operator at site J, which becomes my Gauss law at site J. So I want to set Pj equals 1, and Pj is a projection operator. So now you could ask, what is the obstruction here? So the obstruction is that this gauging would be consistent if and only if the Gauss law at site J commutes with the Gauss law at site J plus 1. And interestingly, you will see that Pj commutes with Pj plus 1 if and only if the phase that I encountered before vanishes. So this shows that the cohomology class of F, which are that 2 cocycle and 3 cocycle, is the 't Hooft anomaly. So I should say that the 3 cocycle obstructs gauging G, but the LSM anomaly obstructs gauging G while preserving the translation symmetry. Are there any questions? So how much time do I have?
5 more minutes since they have 2 questions already.
So now let me give you 2 examples. So let me first discuss the case when your symmetry is on site. I want to show that this procedure reproduces the LSM anomaly for on-site symmetry. So consider a symmetry which act projectively on each site. So my symmetry operator is a product of local factors, U of JG, where U of J only acts on site J and forms a projective representation of G. In that case, you will see that the fusion operator G and H only depends on G, is independent of H, and is just given by these local factors. And then using formula for the anomaly that I gave you before, you will see this equation that alpha, so first omega is 0, omega is trivial is 1, and alpha satisfies this equation. So alpha is exactly captures the projectivity of the representation of the action of the symmetry per site. So you will see that if the symmetry acts projectively, alpha is non-trivial, and that's the version of LSM theorem for on-site symmetries. However, the prescription that I described is more general and also works for symmetries which are not on-site. Okay, let me also give another example. Okay, so a concrete example is just the original Heisenberg chain which appeared in the original LSM theorem. So here you could consider the Z2 times Z2 symmetry of the SO3, which is generated by the sigma x's and sigma y. In this case, the fusion operator is written by this, and because sigma x does not commute with sigma y, you could easily find a cocycle is given by this. So it means that if you preserve the Z2 times Z2 symmetry of the Heisenberg chain, if you deform it, it has an anomaly and cannot have a unique gap ground state, because Z2 times Z2 is projective, is realized projective. Now, so in those examples, when the symmetry is realized projectively, there is no anomaly involving only G. So you could ask, what happens if I gauge the internal symmetry? So as I will argue, is that if you gauge the internal symmetry, which has LSM anomaly, the translation, you violate the original translation symmetry. However, the original translation symmetry becomes a non-invertible lattice translation symmetry. So let me just give you an example in the Heisenberg chain. So let's consider the XYZ chain. For now, just forget about the red terms. So if you forget about the red terms, this is just the XYZ chain with three coupling constants, JX, JY, and JZ. And now I want to consider its Z2 times Z2 symmetry and gauge it. So if I don't add this extra term here, this would be the standard fusion operators. But with this definition, then there is an LSM anomaly. But I could add J-dependent phases, this extra term here, to cancel the anomaly, to trivialize this alpha. So I don't want to preserve translation anymore. And with this modified fusion operator leads to the following modified Gauss law. So here on each link, I'm adding 2 qubits corresponding to a gauge field for the X symmetry and the gauge field for the Y symmetry. So this mu is a gauge field for the Z2X symmetry, is a Pauli matrices that acts on the gauge degrees of freedom for this symmetry, and tau of X is the gauge freedom, is the Pauli matrix that acts on the gauge freedom for the Y symmetry, and leads to this modified Gauss law. And you will see that for this modified Gauss law, now the translation symmetry no longer commutes with the Gauss law. So it means that after I impose the Gauss law, the translation symmetry is not gauge invariant, so I will lose translation symmetry. However, translation by two sides is a good symmetry. So we could actually solve the Gauss law and find this chain. So I've just solved for the Gauss law, introduced new variable. So interestingly, this system have a non-invertible lattice translation symmetry. So the original translation symmetry, which was not gauge invariant, becomes a non-invertible symmetry and acts on the Pauli matrices like this. It's also satisfied this fusion rule, and it's non-invertible because it can map some local operator, not into a local operator, but to a disordered operator. So let me summarize. So I give a macroscopic formula for 1 + 1D anomalies, generalized LSM theorem beyond on-site symmetries, and give you a method for gauging on-site symmetries. And yeah, thank you for the attention.
Great, thanks, Sahand, for the very cool talk. Any questions from the audience?
So Sahand, maybe you mentioned this, so if I have a non-on-site representation of the symmetry, for example, Z2 symmetry in 1D, which could be the edge of this 2D SPT, 2 + 1D SPT, right? You're saying your procedure, you can apply it there as well, although it's not on-site, you can still attempt to gauge it, and you'll find that it's obstructed by the fact that it has the anomaly.
Yeah, so adding gauge field will go on, but I will find that the Gauss law don't commute with each other at different sites. So it will be inconsistent to perform the final step. And the obstruction is given by this, cycle.
So you don't necessarily require the symmetry action to be on-site.
No, it could be general.
Procedure.
Right, I only need to have a presentation of the symmetry as topological defect, which I can prove in general in 1 + 1 dimension.
Nice. Thanks.
I also don't even need to assume that is a finite depth local unitary. So any symmetry that is QCA, which is locality preserving, is enough. Thanks.
Sahand, one more question about the last part. So about this non-invertible symmetry. I thought that once you gauge, say, Z2 cross Z2, you said that T is broken.
T is not gauge invariant, right?
But then you say it somehow reemerges.
Yeah. So there is T tilde. So what T does is not gauge invariant. So it violates the Gauss law. But when you gauge the Z2 times Z2 symmetry, you get a dual Z2 times Z2 symmetry. It's X tilde and Y tilde. So violating the Gauss law is corresponding to inserting a defect for these dual symmetries. So the symmetry, since it's not gauge invariant, it maps a local operator to an operator which is in the twisted sector by this new Z2 symmetries. And that's the hallmark of non-invertible symmetry, that it maps a local operator to an operator in the twisted sector by this Z2 dual symmetries. So that's how I construct this T tilde.
Is it something well known in field theory that, you know, if you have a mixed anomaly and you gauge part of the symmetry, then the one that's seemingly broken becomes non-invertible?
Good. So there are possible scenarios. In most of the cases, when you have two internal symmetries, you gauge one of them, the other one you violate it, but it becomes it participates in some kind of group extension. It becomes a 2 group, or you have Z2 times Z2, it becomes Z4. And in some, for specific anomalies, it becomes non-invertible. So you have all possibilities. But here I'm gauging the other symmetry is lattice symmetry, is a Z symmetry. There is no room for extension. The only possibility here is a non-invertible symmetry. So this statement is general for any projective G. So it just tells you a way to construct many lattice models with non-invertible translation symmetry.
Thank you.
Yeah, thanks for the question.
Yeah, let's take one more question before we move on to the next talk.
I have a question about the generalization to symmetries that are not locally generated. How do you get the defect in that case? Because you can't just transform half of the sites.
Good question. So there is this well-known procedure in QCA is that if your symmetry is not locality, is not a finite depth local unitary, you could add ancillas to making it a finite depth. So I take my system, I add a copy B, then it's a finite depth local unitary. So I consider U tensor U inverse. Once I added this ancilla, now it's a finite depth local unitary. Now I construct my defect, and at the end of the day, I just project out the ancillas by imposing some local projection operator, which sounds like some kind of gauge principle or Gauss law. So this is something that I proved, but I didn't have time to explain.
Thank you.
Yeah, thanks for the question.
Okay, great. Let's thank Sahand again. Let me pause recording and start.